How are you making sure that your secrets are being securely stored so that you can avoid data breaches as well as chaos in your DevOps workflow? Hi, I'm Shruti Anekar and I'm a DevOps engineer here at Velotio Technologies. So let's talk about secrets. Now what is a secret? A secret is nothing but a digital authentication credential that is going to allow entities to communicate and perform actions on a service. Now, this discrete piece of information that we have is going to keep the access points secure. So let's take a look at the way in which this paradigm is going to exist. So an entity here needs access to some sort of a service. We'll leave it ambiguous for right now. There are two things now that an entity will need to communicate with this service. So it is who, that is, what is the authentication that is required and what. So what are the kind of permissions that are going to be required to complete the authentication. So how we enable this is with some sort of a secret. Now that we've established this dynamic that we have right now, let's move into another example. Let's say we have users, and this is a developer A, and they happen to need read-write access to some sort of a repository. So let's say it's a developer repository. So in this circumstance, it is going to communicate by giving a user credentials. Now we're looking forward to cloud native applications. We have a lot of microservices that need to talk to each other. So service A, let's say service A, it needs some kind of it needs to interact with a database and grab a piece of specific information that it needs to get its job done. So what we need in this form is something called as a DB config. But now that we've established everything, like we have our user config, user credentials, we have our DB configs, these are the examples of secrets, we realize the vulnerability that is caused, that it can be created if these were to fall into the wrong hands. So that's why it's important to establish a centralized place to manage all of this. So as we build on the applications, so more applications that we have, more authentication is required, and hence we have more secrets that need to take care of from it. So how we achieve all of this is with secret management. So now what is secret management? Secret management concerns with three things. So first is storage. Like how do we store our secrets? Where is it? Is it a centralized management place? Is it centrally managed? Next is our secret life cycle. So secret life cycle includes creation of secret, modification, distribution, destruction, auditing, tracking the secrets back in time. And the third point is, last but not the least, we have recovery and remediation. So how do we recover these secrets that we have stored if they get lost, and how do we remediate them? Now that we've achieved what secret management is, what does our ideal secret management solution look like? So firstly, it should have security. It should have encryption, that is at-rest encryption, in-transit encryption. It should have fine-grained access control. It should give good access logs. Next is it should be easy to manage and it should be cheap to operate. So it should be central location to operate on these secrets. No more remembering where these secrets are kept. It should be easy to integrate and it should be scalable as well. So now that we've talked about this, let's discuss the levels of complexities that we have in our architectures. So to help facilitate the discussion and visualize how secret management architecture evolves as the team gets better acquainted with technologies, we can define three levels. So here, limited access means secrets are stored in a repository server with limited access to the public. For example, we have a private Git repository. Now, encrypted secrets, that means before being stored in the repository, the secrets are getting encrypted. And third is management. So management, that is an application that allows high-level control of the secrets in which entities can access and audit logs, etc. So these three levels can be seen from an evolutionary standpoint, where the architecture grows more and more from simple to complex as and when needed. So sometimes the concern is rate. Where does this end? So if you encrypt the secrets before storing, where do you keep the encryption key? Isn't that another secret? Aren't you just adding another abstraction layer? So it's a valid question, but not really necessary, right? So we will reach a consensus on how to store an encryption key. So we may choose to employ something called as AWS, or we can rely on other complex mechanisms, which is HashiCorp. We'll talk about them later. So in the end, it's important to emphasize that the goal of secret management architecture should be to achieve acceptable levels of security for the project. At some point, the complexity of the additional layers that we've added, it outweighs the benefits of security, eliminating the security risk. So let's talk about some of the technologies that are used for secret management. So we have something called as a Git Crypt. Now, Git Crypt is an open source project for encrypting files in a Git repository. Now, relying on the webhooks, the Git hooks, files are listed in the Git architecture in our .git attributes files, which are encrypted before the repository is pushed to the remote. Now, to decrypt the file, you would clone this repository and issue a Git Crypt command while specifying the path to the key that can be used to encrypt that was previously used to encrypt. So we have a sequence diagram here describing this flow. So we have a local repository and we have a remote repository. So we initialize the Git and we initialize Git Crypt. Here we specify which files want encrypted in the .git attributes file. You can see an example of the .git attribute files as well. Then we do a git push. Now during the git push, this Git Crypt will encrypt the file and it will push to the remote repository. So on the remote repository, we will only have encrypted files. So if someone requests the clone, we will return the clone and we will return the encrypted files. So what Git Crypt will do is it will unlock these encrypted files, that is, it will decrypt these files. Now the developer can work on these files later on. It can do the local development. So during git push again, the Git Crypt will again encrypt these files and it will git push it to the remote repository. So it's a very practical feature, the Git Crypt, as its ability to specify more than one key for a repository. So this means we can have the prod and the development secrets can be stored in the same place, but only users with access to the correct keys will be able to decrypt these secrets. So example of the .git attribute files. So we have the Git Crypt key encrypting the secrets found in the folder secret/dev. While the Git Crypt/prod key is going to use to encrypt the secrets that are found in the folder secret/prod. There is a common side effect of using this is resolving the conflicts. So Git conflicts are very tricky to resolve when we use this encryption. And when resolving a conflict, we can do a pull remote and do a local diff to support the merge. So that's about Git Crypt. Now, another tool that we will talk about is AWS KMS. So, of course, AWS has a solution for everything, right? And now that we have encryption key management, it is hosted by AWS. Instead of storing secrets, the AWS KMS service can be used to encrypt an encryption key. Why would someone want to do that? Now consider this. Once you have an encrypted version of your original encrypted key, it can't be used to decrypt any of your secrets. Therefore, it's safe to store the encrypted version along with the other secrets. You are free to discard or store in safe backup the original encryption key and trust AWS to be available to decrypt the now encrypted encryption key. So here is a sequence diagram illustrating the workflow. Again, we have plain text secrets. It will encrypt the secret, generating an encryption key. The encrypted secret creates an AWS access KMS master key with access policies. Now the it encrypts the encryption key with KMS key, and it gives it back to AWS KMS. And AWS KMS returns the encrypted encryption key. So the operator can now discard the encryption key that they have, and it will upload the encrypted secrets and the encrypted key to our external server. So whenever a client will now request for the encrypted secrets and keys, it will firstly give the decrypted keys information, the IAM token, and the AWS KMS will return the decrypted encryption key. So it will now use this encrypted key and it will get the plain text secrets. So one of the caveats of the solution is that you become dependent on AWS. So you become dependent on AWS's service availability. However, this will always be some sort of dependencies regardless of the solution. So AWS Secret Manager or any of these will let you quickly rotate, manage, and retrieve database credentials or API keys or other passwords. So using Secret Manager, you can secure, analyze, and manage secrets needed to access the cloud capabilities. So on third-party services and on-premise as well. So secret managers will enable you to manage the access keys to secrets using fine-grained permissions. Now, the key features of this AWS Secret Manager or Azure's Secret Key Vault or Cloud KMS are it encrypts secrets at rest during using an encryption key. Also, it decrypts the secret and then it transmits securely over TLS. Now, it provides code samples that help, like we can call APIs, we can call the Secret Manager APIs. It also has some client-side caching libraries to improve the availability and reduce the latency of using your secrets. So we can configure a virtual private cloud, a VPC, and endpoints and keep the traffic within the network. Now, HashiCorp Vault it allows secret storage with management capabilities. Now, HashiCorp is a very robust secret management tool whose features extend well beyond the scope of this. Like in summary, it serves a secret repository with access control lists and auditing and time to live access to the secrets. Now, Vault supports a variety of authentication mechanisms and secret storage backends, allowing highly available deployments. So here's a workflow of highlighting the storage and retrieval of secrets from HashiCorp Vault. So we have an operator. It sets some policies to HashiCorp Vault. Now these policies will specify read-write access to secret paths. It will associate authentication rules with these policies, the operator will, and it will seed secrets to the path. Now the client, the third party, external one, will request authentication to HashiCorp. So HashiCorp will log the request and it will return the access token if the authentication is successful. Now the client will now request for the secret in the path providing this token that it received. The HashiCorp will log this request again and it will return the secret if it's a valid token and it will do ACL checks as well. So the clear drawback of HashiCorp Vault is the additional complexity that it introduces. So even with a simple setup and limited features, it still requires a member to be responsible for maintaining and managing this access list and vault server itself. However, the benefits are tremendous with higher security requirements. So Vault follows HashiCorp's pattern of elegant solutions and separating different authentication and secret storage backends into independent units. So it allows fine-grained control to the secrets as needed with policies and time to live. So settings can be defined per secret, per group of secrets in a folder. There are n number of such tools in market which will help us manage our secrets securely. A few of the examples which I would like to talk about is a Doppler. So it describes itself as a universal secret manager. Doppler's basic goal is to create a delightful user experience. So Doppler groups secrets into projects with a configurable list of environments, such as it has a development project or dev project, and there is a concept called as branch configs, which is Doppler specific concept, where secrets are inherited from the root config to which they belong. There is another such tool that I would like to talk about, and that is A-keyless Vault. Now, A-keyless Vault is unified end-to-end secret management SaaS-based platform protecting all types of credentials, both static as well as dynamic. So, A-keyless protects the keys and secrets using a built-in FIPS 140-2 certified and patented technology. So, it has a zero knowledge of its customers' secret and keys. A-keyless Vault that we have enables provisioning and injections of all types of secrets to your servers, applications, and workloads, providing a wide variety of plugins that allows you to connect to all your DevOps platforms and IT platforms, such as CI/CD, configuration management, orchestration tools such as Kubernetes and Docker. So you don't have to, the technologies that we described right now about, they don't need to be used in isolation. In fact, they become even more powerful when combined. So we can combine most of these tools that we've discussed right now, and we can use them. To conclude, having a secret management architecture is just one of the steps in the quest for increasing the security in the project.